Folks, for our next speaker, we're very pleased to welcome Michael Vasmer from Xanadu. Michael Vasmer grew up in the UK, where he did his university studies. He gained a Master's of Science degree at Durham University, studying physics and computer science. He then went on to study at University College London, where he began working in quantum information science. He completed his PhD under the supervision of Dan Brown with a thesis on quantum error correction. After graduating in 2019, Michael was a postdoc at Perimeter Institute, an institute for quantum computing in Waterloo, where he continued his research into fault-tolerant quantum information processing under the guidance of Raymond Laflamme. He now works at Xanadu as a quantum error correction researcher and at Perimeter Institute as a research scientist. And with that, while we're getting the slides up, please welcome Michael Vasmer from Xanadu.
Okay, thanks very much for the introduction, and thanks for inviting me to speak here. Yeah, so this is going to be maybe a somewhat technical talk. So I've tried to make it accessible, but it was a long time since I was an undergrad, so please interrupt me with questions at any point. Just feel free to shout out if something's not clear. Yeah, so today I want to tell you about fault-tolerant quantum computation, so how to make noisy quantum processors do what we want and execute algorithms at scale. And I want to tell you the basics of how this works, and then I also want to tell you a bit about the cutting-edge research going on in this area. Oh, wait, that was the wrong slide, sorry. This is the right ones, okay, good. So, why do we want to do quantum error correction? As I think you've probably heard today, current quantum computers are noisy. This can come through many sources, for example, unwanted environmental coupling. There's also a kind of surprising one in superconducting qubits. One of the biggest problems for noise is actually cosmic rays coming and hitting the device and causing loads of the qubits to fail at once. So there's many different kinds of noise. Also, imperfect control. So you're trying to do a gate on your qubits, but it goes wrong. And these noise sources, engineers and people have been working extremely hard to get them down, but it's very difficult to reduce them to the level that you can get in, for example, classical processors, where they're basically negligible. And the noise in current quantum devices really does limit the algorithms that we can run. And what it really limits is it means we can only run low-depth algorithms. So you probably already know what circuit depth is, but I just want to remind you. So the circuit depth here is the number of layers of these gates that we have. So this would be depth 4. And this is the kind of, so you're trying to do as many gates as you can in parallel, but you can't do too many layers before noise completely overwhelms your calculation. Now, these kind of low-depth circuits do have some applications, and there's actually a very interesting paper came out, I think, yesterday or the day before about the computational power of these low-depth circuits. But we know that they're not capable of running something like, let's say, Shor's algorithm, or running these quantum chemistry algorithms at scale. So if we want to do that with our noisy qubits, we have to use something called quantum error correction. And this is a set of techniques which is going to allow us, as long as your noise level is below some certain threshold, using error correction, you can, in principle, run a polynomial depth algorithm. So that would allow you to run something like Shor's algorithm or these large-scale chemistry simulations. But I've highlighted the word here, in principle, because in practice, making this work is actually quite challenging. OK, so I was told this is supposed to be an introductory talk, so I'm going to give you a quantum error correction 101. So the first place where we have to start is quantum error correcting codes. Now, this is the idea is, so we've got k logical qubits, and these are the qubits we want to use to execute our algorithm, and we're going to encode them into the state of n physical qubits, where in general n is going to be greater than k. So it's going to look a bit like this. Let's say we've got 3 logical qubits, and then we apply some unitary, and this is going to encode the state of the 3 logical qubits in the state the eight physical qubits. And the kind of intuition you've got here is that you've introduced some kind of redundancy such that if one of the 8 qubits, there's an error that happens to that, we can recover from that. And we don't lose the logical information that we've encoded in these 8 qubits. Okay, and then there's an error-correcting code also has another important property called the code distance. I won't get into the technical definition of this, but what it basically is telling you is how many errors can your code tolerate. So you want the code distance to be high, because this means that your encoding can tolerate a lot of the qubits having errors, and you can still recover the information. And we're going to use this shorthand, which is very common in error correction. So if I talk about an NKD code, what I mean is this code has n physical qubits, and it encodes k logical qubits, and it has code distance d. And these 3 things tell you quite a lot about the code. And we'll be kind of interested in these parameters and how they behave in this talk. OK. So that's kind of a general picture of what an error-correcting code is. Now I want to tell you about a subclass of error-correcting codes called stabilizer codes, which is introduced by Daniel Gottesman. These codes, you can think of it as using group theory to define a broad class of codes, and the kind of group theoretic description makes them very nice to work with and analyze. So this slide will contain a bit of mathematics, but as I said, anything that's unclear, just shout out. So I'm sure you've seen all these before, but I'm using this notation for the Pauli operators, and then I'm going to define something called the Pauli group, which is, so this is notation just for the group P sub n is generated by just the complex phase. Then it's x sub j means I'm acting with Pauli x on qubit j, identity on all the other qubits, z sub j similar. So what this group is generated by is just Pauli operators acting on each of the individual qubits. And then you can take all products of these as well. So you can get y operators, because that's just I, x, z, etc. So this is an important group that comes up in the study of quantum information all the time. And what we're going to now think about is something that's called a stabilizer group. So a stabilizer group is just a subgroup of the Pauli group, which has some special properties. So the stabilizer group is abelian, and that means that everything in the stabilizer group commutes with everything else in the stabilizer group. So we know that Pauli operators, they either commute or they anti-commute. And it also, importantly, it doesn't contain minus the identity. It's a technical condition, but that's also one of the defining features. Now we can use a stabilizer group to define a code. So I'll unpack this notation I've got here a bit. So I want to tell you what the encoded states of my code is. So this is kind of, if you're storing one logical qubit, this is going to be the logical 0 state or the logical 1 state. So these states are those such that if I act on them with any of the stabilizers, so anything in the stabilizer group, I get the same state back. So you see why this notion of stabilizer is why the language is used, because this state is kind of stabilized by the elements of this group, because they just leave it invariant. And the nice thing is, so the reason the stabilizer group is so powerful, the stabilizer formalism is so powerful, is because this abelian group, you can study its properties by just looking at its generators, and there's polynomially many of the generators, whereas if you were trying to look at the code words, they would be, they're actually a superposition over an exponential number of terms. So that would be very hard to handle, but because of the group theoretic structure, you only have to deal with the polynomially many generators. And an example of this is it's very easy to compute the number of encoded qubits in the stabilizer code. So you just have, so you have this formula where you have the number of physical qubits n, and then you subtract the rank of the stabilizer group. And that's just the number of independent generators. So yeah, that's, and you can compute that very simply, because it's just basically you end up doing Gaussian elimination on the matrix. This is a very important class of codes, and most of the codes that I'll tell you about today, all of them are stabilizer codes, and most of the codes that people think about in quantum error correction theory and experiment are stabilizer codes. yeah, don't worry if all of the details here, if you didn't get everything, it's I just wanted to kind of show you a bit of the mathematics you use to construct these codes. So we'll consider an example now to hopefully make the more abstract stuff on the last slide a bit clearer. So the kind of simplest code you can think about maybe is the quantum repetition code. So I'm going to tell you about this code in the stabilizer formalism, but so the stabilizer group for this, so if you've got an n qubit repetition code, you just have Z1, Z2, and then Z2, Z3, all the way up to Zn minus 1, Zn. So let's say we have these 3 qubits here. We're going to have, the stabilizer group is going to be generated by 2 operators. And also with stabilizer codes, the nice thing is that you can, to actually do the error correction, to figure out if errors have happened, all you need to do is measure the stabilizer generators. Now, I can give you an example of this. So let's say we have these 3 qubits here, and they're in the code space of our repetition code. So just to remind you, that means that they're in one of the encoded states such that if you act on the encoded state with any of the stabilizers, you get back the same encoded state. So maybe I can actually write down what the encoded states are in this code. So the notation I'll use is 0 sub L for logical 0. So this repetition code that we're looking at is a 3-1-1 code. So it has n is 3, k is 1, and d is 1. And the logical states would just look like this. And logical 1 just looks like this. So you can see that for these states in the code space, if I act on this by Z1, Z2, I'm going to get the same thing back, because we know that Pauli Z on 0 just gives me 0. So that means Z1, Z2 acting on 0, 0, 0 is just 0, 0, 0. And the same thing for this state as well, because, for example, let's consider Z2, Z3 acting on 1, 1, 1. We know that Z acting on 1 gives us minus 1. Sorry. Minus 1. And so we're going to get 2 minus signs, so they'll cancel. So we get the same thing back. So these are the encoded states. And as I said, if we want to diagnose errors, measure, and tell that an error's happened, we just have to measure the stabilizer generators. So let's consider this state here. There's been no errors. It's in the code space. So as I said, when we act on it with Z1, Z2, we get back the same thing. Same thing for this generator. OK, great. Now, let's say that actually we had a Pauli X error happening on qubit 3. So now, if we were in the logical 0 state, we're going to have gone to this state instead. And now what you'll see is, let's say we measure the stabilizer generators again. Well, Z1, Z2 is still going to have eigenvalue plus 1, all good. But now we measure Z2, Z3. Uh-oh, we're going to get a minus 1, but it's not going to cancel, so we're just going to get minus this state back. And so this stabilizer will have a minus 1 eigenvalue, and this is telling us that an error has occurred. And this is the general thing you do with stabilizer codes. You measure the stabilizer generators, and then if you get minus 1 outcomes, this is giving you information about what errors have occurred in the system. And yeah, just to emphasize, this code is very bad. So in the talk title, I'm going to tell you about good codes, and I'll say what I mean, because that's actually a technical term. But you can see that this code has distance 1, so it can correct one X-type error, but if you have any Z errors, it doesn't correct them at all. So it's not really useful for anything, but it's a nice example to kind of illustrate the formalism. OK, so does anyone have any questions about this stuff? Because if you understand this, then hopefully the rest of the talk should flow quite nicely. So yes. Yeah, it can correct one X error. There are indeed. The smallest code that you would need to do something like that has 5 qubits. And then there's loads of different codes with different parameters, and I'll tell you about a few more of them today. Okay, so we're now going to talk about probably the most famous quantum code possibly, and definitely the leading quantum code in I don't know, today's both industry and academia. This is the code that people think has got the best shot at being the basis of a fault-tolerant computer, so quantum computer. So I like to think of the surface code as a bit like the truly quantum repetition code, because you can build it from two classical repetition codes using some kind of product structure, and I'll try and illustrate why I think of it like this. So now we've got a stabilizer group again, but it's going to be generated by two-body and okay, that should say three-body, sorry, and four-body X and Z operators. So the way you set it up is you have a grid like this, and what we're going to do is we're going to say there's a physical qubit for every edge in this grid. So I've put them down like this, and then you use the geometry to define the stabilizers as well. So we're going to have a four-body Z term, so I'm using blue to denote Pauli Z operators and red for Pauli X. So for each of the faces of this grid, I'm going to have a Z term where I just act with Z on all the qubits that are in the face. So, you know, I'll get, for these like complete faces, I have the four-body terms. Then for these kind of faces that have been chopped, I'll get this three-body term here. So those are the Z-type stabilizers. Then I will now also have Pauli X-type stabilizers, where for each vertex, I act with Pauli X on all the qubits on the edges that contain that vertex here. So you'll see here I have this four-body one. I also have a four-body one here. And then if I went to the boundary here, I'd have a three-body one, because I'll have X on these three. OK, so this just defines the code. And you can use the stabilizer formalism to compute the parameters. So if we have an L by L grid, so it's not entirely correct for the picture I've drawn there, but the scaling is correct. So if you have L squared physical qubits, then you'll have one encoded qubit. So that's kind of similar to the repetition code. It's encoding one qubit. But now you'll see the code distance is actually L. So this code can protect you against up to L Pauli X or Pauli Z or any type of error, actually. So this is an example of a code that's actually very useful because it gives you good protection against a lot of different errors. And one thing that's an important concept we'll come to shortly is the concept of a logical operator. So it's not enough for me just to protect my information. We want to run algorithms in the end. So we need to also process the information by applying logical gates. So we want to know what these are. And in the surface code, you have these weight L gates, which by weight, I mean it's how many Pauli operators you need. So this is an example of a logical X gate. So it's a four-body operator. And this is going to, if you apply this logical X to logical 0, it changes it to logical 1. So it just acts like you would expect, and then the logical Z looks like this. And what you can show is the logical operators have to span the lattice. They have to go from one boundary to the other one. And this is how you can prove that the code distance is L, because to change one logical state into the other, you have to apply an operator that spans the lattice. And the intuition as to why this is a kind of good error-correcting code, well, is that most noise processors you think of are actually local noise processors. So you think the probability that the environment could apply a very long-range operator is quite small, so that you'd think this code would give you good protection. Now, it's actually quite interesting because cosmic rays is where that falls down, because when a cosmic ray hits your chip, it just causes a massive mess everywhere. And that means that it kind of starts applying logical operators and causes a lot of errors. Yes, and this code, you can sort of see it as like having a repetition code structure in in the horizontal and vertical direction if you kind of squint. And yeah, so this code is kind of due to, well, the original formulation of this was due to Kitaev, and then there's this paper by Bravi and Kitaev where they introduced the variant with the boundaries that I've shown you here. Okay, now I just want to tell you a bit about the error correction we do with this code. So as we said before, to diagnose errors, we're going to measure the stabilizer generators. Okay? So if we have like a state in the code space, a logical 0, we know that all the stabilizer generators are just going to give us +1 eigenvalue. It's all good. But then we're going to say a stabilizer is unsatisfied if when we act with it on the state, we get back a -1. So it has a -1 measurement value. And the error syndrome, just some jargon for the list of unsatisfied stabilizers. OK, so let's suppose that we had a Pauli Z error acting on these 2 qubits. So a Z on the 2 ones colored in blue. Well, now we want to understand which stabilizers are unsatisfied. So you know that Pauli X so Pauli Z operators commute with Pauli Z operators. So it's not going to have any effect on the face type stabilizers because they act as Pauli Z. But it could have an effect on the vertex type ones because remember, for each vertex stabilizer, we have a stabilizer that has Pauli X on the 4 qubits kind of touching the vertex. So what we can do is we can look at these vertex stabilizers. So this one, for example, we'll see that because Pauli X and Pauli Z, they anti-commute, that this vertex stabilizer, which is X on these 4 qubits, is going to anti-commute this error. Same for this one here. This one actually will commute with the error because you get kind of anti-commutation twice, so it cancels out. So the end of the story there is that what we're going to see is that these 2 vertex stabilizers I put the star on are the unsatisfied ones, and these are the kind of error syndrome. So in this system, if this error happens, you'd see this syndrome. And the important thing to note is that we never see the error that actually happened. All we see is the syndrome. So in the real world, we have to, just given the syndrome information, we have to decide what to do. And we'll say that, so error correction, the problem is we've given a syndrome and we need to estimate a recovery operator. And we're successful if the recovery operator is equivalent to the error, but we're allowed that they differ by a stabilizer because a stabilizer acts trivially on the code space. So for example, in this case, we could choose our correction to be Z on these 2 dark blue qubits here. And this would be fine because now the kind of overall thing that's happened is the error, the light blue, and the recovery, their product is just a stabilizer, which acts as logical identity. So we've recovered back to the same state that we had before. So in this situation, error correction has been successful. And the reference there is a seminal paper on surface code error correction by Dennis et al., where they really kind of set the foundation for most of the work on the surface code. So if you read this paper and understand it, you will understand the surface code very well. OK, I think, oh yeah, and the last thing I want to tell you about is, as I was saying, we also need to care about logical gates. And we can't just protect the information, we also have to apply logic gates. And we want them to be fault-tolerant. Now, I won't go into the technical definition of what that means, but basically, if there's errors in the system when we apply a logical gate, we don't want the logical gate to spread the errors around too much. So it shouldn't make the errors a lot worse. And an example of a fault-tolerant logical gate is this logical Pauli Z operator, because if you have a single qubit error and then you apply this operator, it's not going to kind of spread it from one qubit to another qubit because it just acts as a tensor product of single qubit operators. So this is maybe a slightly technical part, but the key takeaway here is that we have to think hard about how to do logic in the encoded space, and it's like a non-trivial problem. But for the surface code, there's been kind of maybe 20 years of work on this question, and there's very well developed techniques for how to do this. OK, and I thought it'd be nice I want to persuade you that error correction, it's not just a theorist's paradise. People are really trying to build these things. And there's been spectacular progress, I would say, recently. So, I mean, it's hard to keep up with the kind of references and what's happening. So I'm just going to give you just a selection. But I've probably missed some stuff. So a very nice experiment from a group in ETH where they realized the surface code in superconducting. This is a distance 3 code. So this is a picture from the paper. So it's like the superconducting circuits, and you can see they've sort of colored it in. And this is kind of giving you the overlay of the lattice like I was showing you earlier. And then there's another paper. So IBM also this is called the heavy hex code, which is kind of related to the surface code quite closely, and it's showing you, the setup with their superconducting qubits, and also now the kind of circuits they were running to measure, like this is measuring the X stabilizer and the Z stabilizer, and then also there's a very nice recent work by Google's group where they realized the distance 3 and distance 5 surface code, so they scaled it up and they saw that they could make the error rate smaller by scaling it up, was the kind of behavior we hope to see. And also, so from example, I know there's been some really spectacular experiments from, haven't got on my slides, but from the Continuum group, building error correcting codes, and they didn't use the surface code, they used this kind of Steam code and things, but that's been extremely impressive work there as well. So yeah, what I'm trying to say is experimental error correction is a really exciting place at the moment where there's loads of cool results and people are really starting to put these ideas that have been in theorists' heads for 20 years into practice, and it's really, really exciting. Okay, so in the last part of my talk, I want to tell you about a new interesting development in the theory of quantum error correction, and then kind of tell you a bit about how I think it could impact the practice as well going forward. So this is going to be another slightly technical slide, so I apologize for that, but we have to define things so I can make good on the promise of the good codes in the title. And what I want to emphasize is all the codes we've seen so far in this kind of technical notion are bad codes. And I mean, so I'll say what I mean. So an encoding rate of a code, so we have an NKD code, and the rate is just kind of how many logical qubits am I getting per physical qubit, so just k divided by n. So you want this to be as large as possible, because then you're kind of getting more value and more encoded qubits per logical qubit. And then the relative distance is also going to be just the code distance normalized by n. And what we want from a good code family is that, so a family of codes, you could think of surface codes of growing size. Now what we want is as we grow the size, we want the rate to kind of tend to a constant, and we also want the relative distance to tend to a constant. And what that's kind of telling you is if you pick a member of the family, then the number of encoded qubits is proportional to the number of physical qubits, and the code distance is proportional to the number of physical qubits. So this is what a good code family is. And you can see that a surface code is not like this, because if we take the rate, it's just 1 over L squared. So as L goes to infinity, that becomes 0. And also the distance, is the relative distance is L over L squared. So that's also tending to 0 as we increase L. So this is a bad code family, and ideally, if we want to construct good code families, because they kind of have the optimal parameters. And there's also another technical definition that I won't get into too much, but it's called the LDPC property. And that means that we want the stabilizer generators to be sparse, so low weight. So as you grow the size of the code family, the stabilizer generators stay low weight. So the surface code fulfills this definition because you always, no matter how big the lattice is, you always have these weight 4 stabilizer generators. So that's another important property, because measuring low weight operators is much easier than measuring high weight operators. Okay, so there was like spectacular recent progress in this area of good codes in the past few years. So finding a good quantum LDPC code was like an open question for 20 years, and basically no one had done better than the surface code up until maybe 2-3 years ago. And then there was a spate of very nice papers culminating in this paper by Panteleev and Kalachev, which won best paper at Stock, which is like one of the leading comp sci conferences in the world, theory. And they solved this question, and they showed that you could find good quantum LDPC codes. And this has inspired lots of follow-up works. So for example, now there's other constructions of good quantum LDPC codes. There's looking at how to decode them. So as we were looking at, you measure the stabilizers, you do error correction. How does that work? And then also a very nice, slightly maybe a more unexpected result is that this good code family was used to prove an open computer science conjecture about the kind of properties that are possible of local Hamiltonians. So it's a really exciting time to work in this area, because there's just like papers. It's hard to keep up with the literature, honestly. There's so many papers coming out about these new constructions and the things they can do. And so I want to highlight some opportunities and challenges when we're thinking about not just the applications of these codes in theory, but actually thinking about the applications to building quantum computers in the real world. So one thing I want to stress is that the surface code has a very big drawback, which is this, that it's got a 0 encoding rate. And that means that, as we saw, that you grow the size of the lattice, but you always have one logical qubit. And what this means is that for the current noise levels, we have to have quite a large surface code lattice. And this means that you need about 1,000 physical qubits per logical qubit, this is basically the entire reason that you see people quoting numbers of, I need 1 million qubits to run Shor's algorithm. Because Shor's algorithm, you need maybe a couple of thousand qubits, but then you have to multiply that by 1,000. And so this is a really big drawback, and it's something that's kind of limiting, it makes fault-tolerant computing further away. Because now getting to 1 million qubits is a very big challenge that I don't think anyone has accomplished so far. So the opportunity is these good codes I was telling you about, they have a much higher encoding rate. So at least in principle, you wouldn't need 1,000 physical qubits per logical qubit, you need far fewer. And if you can kind of make this work, then hopefully you could save a lot on the resources you'd need to build a fault-tolerant computer. But there are challenges, is that good codes, they require non-planar connectivity. So there were nice results that said this is basically, it's essential to have this. So you can't build it in like a 2D grid like I showed you the surface code. You have to have non-local connections, which means that it's not suitable for every kind of architecture. But there are kind of architectures like photonics or ion traps where non-local connectivity is available. So there's hope that these codes could be engineered. And then the second challenge is more of still an open problem in kind of theory of error correction is, even if we have these codes, how do we do fault-tolerant logical gates in a way that retains the overhead and doesn't create too many errors? Because it becomes a lot more challenging to kind of think about how to do this when you have a code where many logical qubits are encoded in the same block. With a surface code where it's 1 qubit per block, it's kind of a lot easier to think about. But when you have many, it's more challenging. And this is something that's a lot of people are attacking this problem, but I would say it's not a solved one yet, and we're still thinking about the best way to do this. Okay, I think that's all I've got for you today. So yeah, those are some Twitter handles you can follow, and I hope this overview of error correction and good codes has been thought-provoking, and please ask any questions. Thanks.